In this video, I wanted to go through a summary for the end of 7B. So in that homework assignment from the class material, we discussed three main equations. The first equation was the either-or probability equation. And remember that if you have overlapping events, you will use addition to add the separate probabilities and then subtract the probability for that overlapping event or for any overlapping events. This wasn't a problem. You didn't need to subtract any probability if they were non-overlapping. In that case, that probability would simply be 0. So for either or probability statements, those are the keywords you want to look for. If you see either or, then you want to use addition and subtraction. If you see and, in those cases, then you'll use multiplication. If the events are independent, meaning that they couldn't happen together, they don't rely on each other, one event has nothing to do with the second event. We talked about with dice. Those are independent events. Tossing die, tossing a coin, those are independent events. So when they're independent, you'll simply just use multiplication between the two, and you'll multiply the probabilities. If you have dependent events, so that one event is dependent on another, we mentioned that that can be tricky, and I'm going to do an example on the next slide to walk you through that. Before we do that, the final equation that we learned about in 7B was the at least equation. So for at least probability, this is easier if you change the problem and use the formula that we discussed. You're going to take, instead of finding the product of the probabilities, you'll take 1 minus the probability that event would not occur raised to the number of trials that you were testing it for. So the three main equations that we discussed in 7B that you should probably write in your notebook would be those three main equations. In this video, I'm going to work an and probability problem where you have dependent events, and these are a little bit trickier. So the homework problem we have here, we're going to find the probability of drawing 3 aces in a row from a standard deck of cards without replacement. I'm starting with a deck of 52 cards, 4 suits, 13 cards for each suit. And we want to know the probability of not just drawing 1 card and putting it back, but drawing 3 cards from that deck. Particularly, we're going to draw 3 aces, or find the probability of drawing 3 aces. And we don't want to do this for the rest of our lives, to test this out, to do experiments over and over. So we are doing this using theoretical probability. So what we need to do is think about the number of ways that this could occur out of the total number of ways to draw 3 cards from a standard deck. If you'll keep that in mind, that's what's happening here. Now, when we're drawing 3 different cards, these are dependent. And the reason is, in this case, I'm not drawing 1 card, putting it back, shuffling, drawing another card, putting it back, shuffling. Those would be independent events. Dependent here, these are dependent because after I draw the first card, that changes the number, that could change the number of aces that are now available, and it changes the number of cards that are now in the deck. So instead of 52 cards on the second draw, I only have 51 cards. Those are things to keep in mind, and that is why this example, these are for dependent events. Now, when these are dependent events, this is not an equation that I want you to worry about, but if you have seen this before, when you have dependent events, all that this means is we're still going to multiply the probabilities between the two events, but when I think about drawing the second card, I have to take into account the first card. So what this is saying, this would just be the equation for drawing 2 aces, by the way. If A were the event, if A represents the event of drawing an ace and B represents the event of drawing an ace, then the event of drawing 2 aces would be the product of the probabilities here. This is the probability of drawing an ace times the probability of drawing a second ace given that the first was an ace. So that's what this little line here means. It means given that. So this is the probability of drawing a second ace given that the first card drawn was already an ace. And that's what we have to consider. So when we have dependent events, each time we multiply a new probability, we have to consider what happens in the previous event. So this is an and problem. We are going to multiply but this is done slightly different than just some of the previous problems because we have to take into account what happened on the previous two draws. So to get into this probability, I'm going to write this out. Same problem, finding the probability of drawing 3 aces in a row from a standard deck of cards without replacement. For the first card, there are 52 cards, and I apologize, this is my handwriting. There are 52 cards available in the deck, and there are 4 aces available in the deck. So for drawing the first card, this would have been a problem like we would have had in the 7A assignment. It was a 1 out of 13 chance that we would draw an ace from the deck. And if you think about that, one suit has 13 cards, 13 types of cards, and one of those is an ace. So this makes sense. 4 out of 52 is simply 1/13. The first card, we would have done this part in 7A. So this should be pretty straightforward. The second piece here that we're just now learning, though, this 3/51 is because there are 3 aces remaining in the deck now that we've taken one out, and there are only 51 cards remaining in the deck now that we've taken one out. So this second probability, while we're still multiplying, it changes. It's not just the same as 1/13 as it was for the first one because we have to change that for the first event that occurred here. So 3 out of 51, if you divide 51 by 3, you get 17. So I've gone ahead and simplified that below. 2 out of 50 is your third because you have 2 aces remaining in the deck and 50 cards remaining in the deck. 2 out of 50 simplifies to 1/25. When you have an and problem, I do want you to multiply. That is the right step. So I could have multiplied the first 3 fractions, but I would have had I would have had a bigger number in the numerator and a very big number in the denominator. Since I simplified those before I multiplied, so each of these that are below, the fractions below, are completely equivalent to what is above, but since I simplified those, then now it's a little bit easier to find that product. So 1 times 1 times 1 is 1, and on the denominators, 13 times 17 times 25 is 5,525. So this would be my final result. So this was an example of using the and probability concept for dependent events.